Okay, students, welcome to the lecture for September 13th, 2019. Anyway, need you all to watch this lecture. Those of you that have watched it need to tell others because we need to keep going. So right now we're in the Krauss book and we're in chapters 5 and 6 now. Some of the materials we're going to cover today, that's dealing with martensite and bainite and some other microconstituents in steel. So need to keep reading. So to remind you what we talked about at the end of last class period, remember I presented two continuous cooling transformation diagrams. One was for a steel that had a very small amount of carbon. So 0.2 weight% carbon. And one was for a steel that had 0.8% carbon. And one of the things that we said was when you add more carbon and alloying elements, it pushes this to longer times and down so that the martensite start temperature and martensite finish temperature get lowered. So going on to the next slide, there are relationships that exist. So we'll just talk about MS and MF temps. There are relationships that exist for sort of estimating these temperatures based on the composition of the steel. So one of those, there's several out there in the literature. One well-known one is called the Andrews equation. And it looks something like this. There are some other ones out there. So the martensite start temperature in degrees C equals, here I'll just write the equation and then we'll talk about it. Minus 12.1 chrome content minus 7.7 nickel content minus 7.5 molybdenum content. Anyway, taking a look at that equation, what you can see is carbon has the largest effect. And then you can see some of these other alloying elements reduce the martensite start temperature to varying degrees. So that's kind of what that equation does. And some of you realize that there are relationships, say, with hardenability of steel, that you plug in different percentages of alloying elements and it changes the hardenability. Well, same thing here. So the bottom line is the martensite start and finish temperature are lowered with more and more alloying content. So that's important. Now I wanted to talk a little bit, and there's a handout that I sent to you by email on how do we actually determine the MS, martensite start and martensite finish temperatures. How do we do that? So this is analogous to how do we determine where the boundaries are on the isothermal transformation diagrams for, say, perlite, where we sort of watch and hold what happens. There's sort of two main approaches. One is, we'll call it, the first approach is a metallographic approach. And essentially that's a lot like Bain's experiments that we described the other day, where you do different heat treatments and then you look at the microstructure after and you kind of deduce what was going on at different temperatures. And so I'm gonna draw a continuous cooling transformation diagram and to describe this approach. So here's our continuous cooling transformation diagram, right? Temperature and log time. And the approach is essentially this. You cool down to a certain temperature, so you see my line going down. You get down to a certain temperature and then you hold for a little while and then you quench down to room temperature. And so you do that at varying temperatures. So maybe you do another one, you go down to this temperature, you hold for a while, then you quench down to room temperature. And the idea is you look metallographically at the products that you get at this point when you cool down to room temperature, and you can essentially see a mixture of different areas in the sample. I'll just draw it like this, where we've got sort of what we'll call fresh martensite and tempered martensite. And they etch differently. So how do we get these different areas of what we call fresh martensite and tempered martensite? Well, you can see you get a certain amount of material that forms martensite here, and then when you hold at that elevated temperature, that martensite gets tempered. So now we're here, and then when we quench down to room temperature, whatever was still austenite gets converted to fresh martensite. So the idea is you can cool to these different temperatures, and we're going to see this on the next figure, which is from one of your handouts. You can cool down to these different temperatures and hold for a small amount of time, and then cool down to room temperature, and then you can actually visually, after you polish and etch these, see very well the different percentages of, sort of what we call tempered martensite to fresh martensite. So if you look over here at the right, you can see up at high temperature, not much is transformed, so not much is tempered martensite. That's in this figure right here. And then more and more and more as we go down to lower and lower temperatures. So you can measure the relative sort of amounts here, and you can deduce where these sort of, martensite starts and martensite finish temperatures are. So that's one way, experimentally. The other way is what we'll call a dilatometer approach. So this is an experimental way of measuring volume or length change. So remember we said when we have a transformation to martensite, there's a volume change. So what we can do is conduct experiments to measure the elongation or length of different samples when we do these different heat treatments, and we get sort of a curve that kind of looks like this. Where this is temperature down here. So here's maybe 100 degrees C, 200 degrees C, 300, so on. So as we cool down, we get this different, volume length change. So here's where we'll mark the Martensite start temperature, and here's where we'll mark the Martensite finish temperature. So anyway, just want you to know what's behind those diagrams. When we look at those CCT diagrams, we're looking at these time temperature transformation diagrams. We're looking at experiments that have been developed to see, what temperatures things are transforming at, and then in case of, say, perlite, how long does it take, which is what we did last time. Now, one of the things that we were hinting at the end of last lecture was this concept of retained austenite. And so basically the question that I hinted at was, what if the Martensite finish temp is below room temp? So in other words, here I'll just draw a little bit of a diagram here. One of those CCT, one of those isothermal transformation diagrams that we've seen. So what if the Martensite finish is way down here? And room temperature is right here. Well, when we quench down to room temperature, you can see that not all of the microstructure transforms to Martensite, and so we can have retained austenite that is around after our heat treatment. That's austenite that is still around at room temperature. We didn't talk much about that in MET 232. So we can look at the fraction of sort of Martensite transformed in a steel that we rapidly cool and quench. And we get this equation that looks like this. The fraction is 1 minus, it's dependent on temperature here, delta T, where delta T is the undercooling below the Martensite start temp in degrees C. Well, what it's saying is the more that we undercool, the more fraction transforms to Martensite. But like we said, if the Martensite start and finish temperature are too high, then we can have a significant fraction of retained austenite left. So going to the next slide here, we could represent that this way. We could look at retained austenite sort of fraction. And it looks like it's basically 1 minus F. So we could look at a schematic of the volume percent of retained austenite versus, in this case, carbon content. So here's 10%, 20%, 30%, so on, retained austenite. And then with carbon content, here's 0.4, 0.6, 0.8% carbon, 1% carbon, so on. So this is weight percent carbon in the alloy. And we get this curve that looks like this. So again, this is the thing to note here is the retained austenite increases with carbon content, and we'll say and alloy content, right? To go back to what we talked about, the martensite start temperature and finish temperature are lower and lower with more and more alloy content, so there's going to be more and more retained austenite around. Now, let's go on a little bit, and let's go to a figure that I think is on one of the handouts that I sent. It's a really important figure here. That's this figure. Let's talk about the figure on the left. So the figure on the left is just what I drew, which is how much retained austenite is around for different carbon content, plain carbon steels. And you can see it increases with more and more carbon content, right? That's the trend. But the effect is shown on this figure on the right. So I want to talk about this figure on the right. It's a really important figure. It shows you the hardness of different steels at different carbon contents. And so you can see the hardness of slowly cooled steels and spheroidized steels down here. It's really low as a function of carbon content. But you can also see the hardness of sort of martensite increases with carbon content, but then all of a sudden this curve breaks here and there's this cross-hatched region over there. You can see that up here. Well, what that is about is you can see that when we start increasing the carbon content, we get to a point where if we look at this part of the curve, it sort of levels out at about 65 Rockwell C. This upper curve is where we could get to if we could transform all of, the whole microstructure to martensite. But the reason this levels off is related to this curve over here. That is, once we get above about 0.6 or 0.8% carbon, we start to have a lot of retained austenite. And that retained austenite is not very hard, it's very soft. So what that crosshatch region on the right represents is sort of the area that we could get to if we could transform everything to martensite. But if the martensite start temperature is below room temperature, that may be difficult. So let's talk about some of maybe the benefits and of retained austenite versus detriments here. So the benefits here of retained austenite, benefits. It's a couple benefits. One is it improves the toughness and ductility some. That is because austenite's much more ductile than martensite. So we might want some retained austenite around, otherwise the part gets too brittle. One area that is important in is, say, the production of bearing steels that make bearings. You want bearings to be really hard and wear resistant, but if they're too hard and too brittle, if the bearings get loaded too quickly, they will break. So we might want a little bit of toughness built in. The other benefit is this type of steels they call trip steels, and that stands for transformation induced plasticity. And that is, we talked about martensite being a shearing transformation. Well, if we deform a metal that has retained austenite in it, some of it can transform to martensite. So it's almost like the thing gets stronger as we're deforming it. Okay, now those trip steels are a little more complicated, and we may talk about those down the line, but that's kind of the gist. So that can actually kind of help us. Some detriments here are just what we said a second ago. The primary one is we can't hit the hardness that we want to get to. We can't reach the potential hardness that we can get to. And the idea is, under certain circumstances, it can transform to fresh, what we'll call fresh martensite. I've been using that term a couple times. So we'll say under certain circumstances. Now, what does that mean? This whole fresh martensite. Fresh martensite is super brittle, so it's untempered. So let's say that I have a steel that I've quenched and tempered, but yet some of the austenite is still around. Under the right circumstances, it can transform to fresh martensite, which is really, really brittle. And then, as someone mentioned in class last time, this can really affect the dimensional stability of a steel. So if we have a steel where we need it to be dimensionally stable, like gauge blocks, or there's lots of different applications. If the retained austenite transforms after, under certain circumstances, then the there's a volume change, like we talked about. So it can be beneficial, but it can also work against us. Now, let's talk about, so we're going to switch gears here, because now we've been starting to talk about austenite. So let's talk about austenite. I believe this is in chapter 8 of Krauss. So this is chapter 8 of Krauss. So we're going to talk about austenite. We already know it's an FCC iron phase at high temperature, but I want to introduce this term, austenitize, for a steel, and what that means is we hold in the austenite region long enough to form austenite. This is the basis of almost all heat treatments of steel. So this is the starting point for heat treating and controlling microstructure in a steel. So it's important, and we didn't talk about this at all back in 232. We just said, oh, you heat up into the austenite region. Well, what we're going to talk about now is, what do you have to worry about? How long, microstructure, how long do things take to get to austenite? Doesn't happen immediately. So when we're talking about heat treating steels, we've got to get up into the austenite region, but what are our other concerns when we're transforming to austenite? So we're talking about heat, we've got to heat long enough. Or in other words, how fast do things transform? We've been talking about how fast do things transform when I'm going from austenite to something else, cooling down. Now we want to talk about going the opposite way. So, you do austenitizing for sort of two reasons, and we kind of summarized them up here. But the first region is called homogenizing a steel, or sometimes this is called soaking, and it's to try to kind of get a uniform composition in the steel. We hold up in the austenite region so that diffusion can occur, so we can even out all the alloying elements. And then the other, like we said, is heat treating. It's the basis for heat treating to control the microstructure and properties. So it's important. So what we're talking about, let's go to a phase diagram. So here's our phase diagram from the Krauss book, iron-carbon phase diagram, iron-iron carbide. If we go back to this diagram, we're talking about heating up into this region for a steel, right? Austenite region. But what I'm going to spend a few minutes talking about here is, where do we heat in the austenite region and how long to form austenite? Again, it's a diffusion controlled process. So let's just say we have a slowly cooled steel. The microstructure we would predict is alpha ferrite and iron carbide, alpha and Fe3C, right? Well, those alpha and Fe3C perlite looks like this. It's got regions of low carbon alpha and high carbon Fe3C, but we're talking about transforming it back to austenite, which has a uniform composition. So it takes a while. Diffusion has to occur, right? We're talking about going the opposite way that we were before. So let's go on and let's talk about some important considerations. So the idea is, this is the transformation to austenite. Is like the reverse of perlite transformation that we've been talking about too. That is, we're heating up. So we're talking about going from perlite, so here's a perlite microstructure, transforming, maybe a little bit transforms here. So what I'm showing here is, this is upon heating, right? Not cooling. So upon heating, now we have perlite. Now we get a little austenite in here, right? And then the rest is perlite. And then finally, if we hold it long enough, it's all austenite. So now it's all austenite. So it's the reverse of what we're talking about. To put this on a phase diagram, maybe we could draw this. But now we're talking about going this way instead of from high temperature to low. There are also time temperature transformation diagrams that describe this. So let me go back here for the steel. Let's extend this dotted line. So this transformation line here looks like this. Depends on temperature. And the idea here is, we're talking about going up to a temperature above into the austenite region and holding, and watch what happens. So over here it's perlite, and on this side it's austenite. So it starts transforming here and it ends here. And just like we saw with the transformation of perlite, we could look at the same thing. We could look at the fraction transformed here. So it starts right here, and then it's finished after this amount of time. Right? Fraction transformed over time. But you can see for the most part now on heating, the higher that we heat, the faster that it transforms to austenite. You can kind of see that from the figure in the upper right, which kind of makes sense, right? It's diffusion controlled. If we were to take sort of a detailed look at this, transformation of perlite, so we're talking about going the other way, like we said, perlite going to austenite, there are some sort of steps along here. We kind of describe it like this. You know, things transform to austenite here, and then there are these regions here that have not transformed yet. We're going to call this austenite with sort of undissolved carbides. That is, not all the carbon is back in solution yet. And then if we hold it for longer at higher temperature, finally it's all, you know, transformed. Sometimes they call this this austenite with undissolved carbides, they call this unhomogeneous austenite. In other words, we have regions that are sort of austenite at the equilibrium composition, and then we've got austenite that's got, you know, different amounts of carbon or these undissolved carbides. Here's a homogeneous austenite over here. So we'd say all austenite. Homogeneous. But the key things to remember, a couple things here. It's controlled by diffusion. And so it's, you know, temperature and time are factors. So the longer I hold it at a temperature, more austenite's going to transform. Or the higher temperature I hold it at, the more quickly things are going to transform. Makes sense because it's diffusion controlled. Now, practical implications for heat treating, and I want to write a few things down here and show you a couple figures from the Krauss book. So what's the practical implications for heat treating or so-called austenitizing a steel? Well, first, we could talk about one, how long to austenitize. How long do I hold it up in the austenite region? Well, there's a lot of factors here. First is how thick is the part? Why is that a big deal? Because it may just take a lot longer to get above the austenite temperature. And then we could look at, like we just did a second ago, how long does it take for perlite to go to austenite once we get above that temperature. So the first thing I wrote, how thick is the part, is related to how long does it take to get to temperature, and then once it's at temperature, how long does it take for perlite to transform to austenite. So again, this leads to what we'll call transformation diagrams for austenitizing. This is definitely something new. We've seen transformation diagrams on cooling. This is on heating for austenitizing. And I'm going to show you a couple of these from the books, but to sketch it out, what they kind of look like is this. You got different temperatures. You know, here's maybe 700 degrees C, 800 degrees C, 900 degrees C, so on, 1000 degrees C. So we're heating up in the austenite region. Here's temperature. And then we've got log time. And what we said is the curves kind of look like this. But we've got these boundaries on here. So we've got, you know, over here, alpha plus Fe3C. Then maybe you have austenite plus Fe3C when we get beyond that boundary. And then we've got this, what we called inhomogeneous austenite. And then finally, homogeneous austenite here. So let's just say I heat it up to 900 degrees C, right? This is log time, so maybe you have, you know, a certain amount of seconds, 10 seconds, 100 seconds, so on, 1000 seconds. But let's just say I heat it up to 900 and I hold and watch what happens. It takes a while to become homogeneous austenite, and there are steps on the way. Again, this has implications for practical heat treating. So let me show you some figures from your Krauss book, chapter 8. You can see these time temperature austenitizing diagrams for different alloy steels. You see what temperature you have to get to, how long you have to hold. So looking at this, 4200, this 4140 steel, you can see, well, you've got to get up above. First of all, they've marked the the A1 temperatures and things like that, important temperatures for transformation. But remember, we talked about AC temperatures. That is, upon heating, the temperature where things start to transform can change depending on, the rate that you heat. So you can see where those apparent temperatures are. But basically what this gives you is a map of, okay, if we treat this part at 900 degrees C, how long do we have to hold it in the furnace for it all to transform? You can see for, this steel, it's much quicker than for this 52100 steel. In fact, for 52100, we start to get so far, here, let me draw this, for 52100, we start to get so far over here that we actually have to get to a much higher temperature to get austenite than we do, say, for this steel right here on the left. Good. But the point is, there are maps out there and there are heat treating guidelines based on this. Now, the other question, so back here we had question 1, how long to austenitize? The other question is this: what temperature to austenitize at? So what temp to austenitize at? Well, the answer is the lowest temp possible for several reasons, which we're going to go into. One is energy use, but the other is a minimization. You want to minimize the grain growth of austenite. Now let's recap a 232 principle. You guys remember the whole idea of, grain growth. So we talked about, for a cold worked metal, we talked about recovery, recrystallization, and grain growth. Well, in the case of phase transformations, things transform. They start out as small grains and then they continue to grow. So if I hold up to a very high temperature in the austenite region, the grains will very quickly grow. And there's data out there to look at the austenite grain size. So we'll call this gamma grain size as a function of sort of time at different temperatures. So here's time on the x-axis. And you get curves that kind of look like this. So let's see, here's about 800 degrees C, 900 degrees C, 1000 degrees C. It follows a relationship that looks like this. This grain growth follows the relationship d squared minus d0 squared is equals kt. Now let's define the terms here. But this is the grain diameter after a certain amount of time. D0 is the starting grain size. Starting grain size. And K is a constant that depends on temperature. So constant depends on temperature. And here's the time. Little t is the time. If you make the assumption that the grain size is small to start with, D0 is really small, then this kind of reduces to this form of this equation. And if you take a look at the curves that I've drawn there at the different temperatures, they look like, you know, sort of a square root of t curve. Okay, it goes up as the square root of t. Now, let me show you a figure from your book and talk about this. But this concept is really important in heat treating steels. That is, the austenite grain size really controls a lot of what you get in a steel. So we normally want it as small as possible. There's several reasons for that. But the prior austenite grain size controls a lot of properties and the microstructure. And the finer that we can make the microstructure, usually the stronger and tougher the steel is. Now let me go to a figure from the Krauss book, chapter 8, that I just kind of sort of drew there, and that's this figure. But what this is showing, the implications of this, this is the austenite grain size. But I want to note austenite grain size really starts to take off or get large or big when we increase the temperature up into that austenite region. So you can see down at 8 or these curves here are at 900 or 1000. They don't grow very fast. So we can keep it at temperature for quite a while. So that's these curves down here. They don't grow very fast. But once I start to get up to 1100, 1200, look at how quickly the austenite grain size just starts to get really large very quickly. That is not desirable. So that's another reason that when we're talking about austenitizing a steel, we usually just want to get up just here a little ways into here, not way up here. It doesn't do us any good. In fact, sometimes it really messes up the microstructure that we want to get to. So it's an important concept. And on the next page here, let me just reiterate that. We want smallest austenite grain size possible in almost all cases, because it affects TTT diagrams like continuous cooling and isothermal transformation diagrams. That affects nucleation. If the austenite grain size is smaller, we have more nucleation sites. And then also, the microstructure that you get to, that you inherit, is finer in the end, like we said. And then this also affects the hardenability of a steel. So it really has implications for heat treating. Okay, good. Now, so that's kind of some new information on austenite. We didn't talk much about that. We just said for heat treating, we heat up into the austenite region. Didn't really say much more than that in 232. Key takeaways here are, we've got to heat it up there. It's got to be a certain amount of time. So when you go and look at these heat treating guides for things, it tells you, how long you've got to heat it up there. Where to heat it, because it depends on the steel and the composition. And we don't want to overheat the steel, because then the austenite grain size gets way too large. Not desirable. Okay, good. Now we're going to switch gears and we're going to talk about bainite, which someone mentioned at the end of class, or asked me, are we going to talk about bainite? And the answer is yes. Here we go. So bainite is, let's do a definition here. It's an intermediate microconstituent or microstructure in a steel that's sort of between perlite and martensite. And if we look at our isothermal transformation diagram that we've been looking at, this is the A1 temperature here, that dotted line. That's the transformation temperature. Right, we have these curves. We've already talked about perlite, so perlite looks like this. And then also, so this is austenite going to perlite. But if we get down to lower temperatures, we have this region here that sort of looks like this. And then we've got our martensite start and finish temperature. And this region is where we can have austenite going to bainite. So often in the isothermal transformation diagrams that we've been looking at and seeing, these are kind of combined so that you see the overall transformation kind of combined like this. And there's this sort of dotted line here, and we say above there austenite goes to perlite and below austenite goes to bainite. But you can see from the diagram to the left, it's not such a well-defined thing that's going on. You may get a mixture of in the middle there, you may get a mixture of perlite and bainite. But let's talk about what it is and sort of how it forms and maybe some implications. So schematically, let's talk about a schematic drawing of the formation. We said it's kind of like intermediate between martensite, where we trap all the carbon in solution, and perlite, where the carbon comes out of solution in the form of austenite, in the form of iron carbide, Fe3C. So a schematic of this transformation kind of looks like this. We have all austenite, And then on cooling, we get sort of these needle-shaped formations like this. It's kind of like martensite. So we get this sort of what we'll say needle-shaped ferrite. And in there we have these small flakes or rods or particles, kind of depends on the temperature, of Fe3C. So we've got these little Fe3C, we can say flakes, rods, or particles. But the point is they aren't big layers of Fe3C like we saw with, perlite, right? Like this. It's not like this. So we're kind of in between. Now the reason that it forms these sort of needle shapes, and the reason it forms the flakes and particles is because this is a diffusion controlled process, and so we get these diffusion kind of fields that we'll talk about as this alpha. Here, we'll talk about this right here. As this alpha needle sort of grows here like this, you get these sort of diffusion fields of carbon around here that sort of control what's going on. Now, let's talk about bainite morphologies here, and I'll show you some pictures here. So next, the next figure I'm going to show you on a CCT diagram, we'll talk about TTT diagram, bainite morphologies. Right, we said it could be rod-shaped particles or flakes or whatever. So here's our temperature, here's our time, and here is the curve we've been drawing. Well, we said, up here, this was austenite going to perlite, and so the microstructure here would be like a coarse perlite. Microstructure here would be fine perlite. Then when we get down to this region, we have a region we call upper bainite. And as we get down to lower temperatures, we call it lower bainite. And as you can probably predict, the lower temperature or lower bainite starts to get more martensite-like, where upper bainite is maybe a little more perlite-like. But this is an intermediate microstructure, like we talked about, intermediate microstructure. So on the last figure that I drew, we could maybe summarize that you have both, go to that one here in a second, shearing and diffusion going on, both. Bainite mechanical property wise is an interesting microstructure because it has both good strength and good toughness. Now here is a figure, sort of classic figure that shows bainite, sort of upper bainite versus lower bainite. But you can kind of get the idea. You can see for the upper bainite, you almost start to get little cementite layers, but not quite. There's more like flakes here. Here, I'll kind of shade them in dark. It's kind of these like flakes. And then on the right, you can see lower bainite. We blow that up. Now it's this sort of shearing transformation here where we get tiny little particles of Fe3C in there. Other sort of difference here, so let me do a schematic of upper versus lower bainite, upper bainite versus lower bainite. Upper bainite is a little more like these little ferrite crystals in packets like this with, we'll say, Fe3C rods in between. Here, I'm going to try to draw those in between there. So we get these like ferrite crystals in packets, and then in between them, so if I could blow this up, it'd look like this. In between, we get these little sort of Fe3C rods. And then lower bainite is a little more like, you know, martensite that we've been seeing. We'll say maybe more random needles of ferrite. And then the Fe3C in there is more like really small particles, Fe3C, small particles. Now, as we're going to see for practical heat treating, it is tough to get a microstructure that's all just bainite. But it can be done, and sometimes it's very desirable because, like we said, it's a good mixture of both strength and toughness for a steel. So let me tell you, one last slide on bainite. So let's talk about bainite in alloy steels. And what happens to the TT diagram, or the isothermal transformation diagram. So here's a plain carbon steel. Plain carbon steel. It's not a whole lot different than what we drew here. We'll draw it like this. We got perlite, right? Perlite. There's not a whole lot of sort of distinction between these two regions. They kind of blend together, like I drew before. But as we get to alloy steels, something that you could note about what goes on here is it tends to really, not only does it move things to longer times, it really tends to sort of separate out these regions. So we can say it like this. Here's our perlite region, and here's our bainite region. So it tends to separate them. Good. Okay, again, chapters 5 and 6 are important because they talk about, in Krauss, they talk about martensite details and bainite. So you need to keep reading. And Krauss is a good book. The chapters aren't long, and it's pretty readable. So it's a good book to read. But you got to stay on it. Now, I've got a question for y'all. We're going to spend one last time on a microstructure in steel that we're going to talk a little about. And that is microstructures that look like this. And so what I want you to do is look at this microstructure and just kind of say, what is this? Guess what this is, maybe. So maybe you can look at this for a second and go, what does it look like? Well, let's talk about what this is. So this is a microstructure in a steel. And you kind of see what kind of look like needles in a way. And so I want to talk about this steel, these types of steels in particular, because you may look at this and go, well, what are these needle shapes here? Are these martensite? Is it something else? Is it bainite? So we're going to talk about this. But the answer is, this is a mixture of ferrite and perlite. Okay? Now, I know we haven't seen steels and talked about this a whole lot, but this is a mixture of sort of what we call ferrite, acicular, which I'll talk about that in a second, and the gray is perlite. But this looks a lot different than a slowly cooled steel. So I'm going to talk a little bit about this microstructure and then we'll quit. So this is for hypoeutectoid steels. What does that mean? Well, you should know what that term means. It means we're to the left of the eutectoid temperature. So those are steels that have, lower than 0.76% carbon. These are ferrite microstructures. So the microstructure a second ago, it looks kind of weird. It's a ferrite microstructure. It's not martensite or bainite, even though we have these weird morphologies. What we can say here is based on cooling rate, you can get a variety of ferrite microstructures. So, sometimes they, one of the classic microstructures that we've already looked at is this microstructure here. So what I'm showing you here is a schematic from the Krauss book where we have austenite transforming to ferrite. And this is so-called polygonal because it looks like a polygon. This is our normal ferrite, like big chunks, ferrite grains. But depending on different cooling rates, we can get things. So here's sort of austenite transforming to ferrite here. So again, here's austenite out here, and here's ferrite. But if we start increasing the cooling rate, we get this sort of needle shapes that start to form. Again, that's sort of based on what's going on with diffusion. And I'm going to show you a schematic of that here on the next slide, and it's from the handout that I sent you. And then, we start cooling faster, and we even get these other morphologies where the ferrite starts to look like this. They call this acicular. That's a term for today, new term. It means needle shape. So sometimes this is also called Widmanstätten ferrite. So named after this guy, Widmanstätten. You can see some of these kind of weird sort of shapes in meteorites, it turns out, because they have kind of strange cooling rates sometimes. You get this sort of needle-shaped patterns. That's shown on one of the handouts I gave you and on this next slide here. Here it is. How different types of ferrite can form on the austenite grain boundaries based on diffusion of carbon. So you can see this needle of sort of alpha shoots out here, and the reason it does that is because of the way carbon diffuses around this. So I highlighted this carbon diffusion fields. But the idea is, going back to these grains of austenite, we'll draw them like this. Here's 2 grains of austenite. We get this ferrite that nucleates on the grain boundaries, like this, and then sort of shoots ahead here based on this diffusion field of carbon in front of it that we talked about. So read a little bit about those. We're not going to spend a whole lot of time talking about different ferrite microstructures, but you need to be able to recognize that kind of thing. And what are the conditions that we see these kind of different ferrite microstructures? To sum those up, what conditions do we form some of these, for these different ferrite morphologies? My writing's getting bad. It's probably time to end the lecture. So we'll just say it this way. If the austenite grain size is really large, so big sections of steel and things like that, we can say here the ferrite nucleates inside the austenite grains because there's not a lot of nucleation sites if it's large. Like we said before, rapid cooling rates. So sometimes we see these types of microstructures in welding, this kind of weird ferrite morphologies. And remember, carbon, the whole gist is carbon diffusion fields. The reason we have these different morphology is we'll say ahead of these ferrite alpha needles. Again, castings and welds see these kind of strange ferrite microstructures. Castings, especially large castings, can see this. Welds, because of the rapid cooling rates. So just important, but I want you to be able to recognize those. Now we're going to get into heat treating of steel in great detail soon, but we're just talking right now about the basics of perlite, bainite, and martensite. What are they? What conditions do they form? And pretty soon we're going to start talking about practical heat treating next week. So excellent. So I hope you stuck with it. Hopefully you watched this on, like double speed because I was so slow. And I will see you next week.